Okay, so today we'll be starting this topic of charged particles, right? Before we do so, is there any question from the previous worksheet? Actually, I think I did not share that worksheet with you guys. Can you remind me if I shared it in the beginning or
Yeah, you
the
did it.
worksheet? I did share. Okay, so I'll share the solved version of it as well that we solved in the class. And if there is any question, just go through it and feel free to ask. So let's start this topic of charged particles. Let me just give me a second. Okay, yeah. So you're already familiar with charged particles. We know it just means that we have a particle that is charged, and the most basic charged particle that we know of is an electron, right? And we know electron is a -1, carries a -1 charge. We have encountered these electrons and their dynamic behavior as well previously when we were studying electromagnetism. And if you remember, we had something like this. If you have a wire, so this is a zoomed in version of a wire, and suppose that there is some current flowing in this wire, right? Some current I that is flowing in the wire. What do we know about that? We know that current is just the number of charges that are moving per unit time, right? So in a particular space, how many charges that I have that are moving per unit time, that specifies the current, which means that this means that there would be electrons in this wire, which would be moving in the direction of the current. There are two different directions, conventional current and the actual real current. We'll be following, I'll be at least following this one, that the current is in the direction of flow of electrons. Now, we know that there will be, if the electrons are moving, what would happen to these electrons in the wire? They would experience a force, right? They would experience a force, and that's also something that we already know. When charges are moving, they'll experience a force that is perpendicular to the direction of motion. So let's suppose that this is the perpendicular drop, and so they would experience a force in this direction. So then this means that the force that is experienced on a current carrying conductor by the electrons is due to the moving charges or electrons in that particular conductor, right? Now we'll look at the equation that we have already seen before. Remember this equation, that this force F was given as BIL. Let's should I use small I? If I did small I, then I'll use small I here. And because the force is perpendicular to the direction of the motion of electrons, that means that this is the sine theta component, right? So usually you will just take the theta as to be 90 degrees, and this just reduces to BIL, because sine 90 is 1. Right. The reason that I add this sine 90 over here, by the way, is if you remember, we did one example where the conductor was placed at some angle to the magnetic field and not just perpendicular. So in this case, suppose if the magnetic field, just for illustration purposes, is in this direction, then only the perpendicular component of this current will contribute to the magnetic force, right? The horizontal component will not contribute. So is that clear? So you're all familiar with this equation, right? F equals BIL. It just tells you that the force that is experienced on a charged or a current carrying conductor is proportional to the magnetic field, the current that is flowing through the conductor, and the length of the current carrying conductor. So if the wire was longer, the force experienced would be large. If the current was higher, then also the force experienced which would be large. Now, there's another equation that we are already familiar with. If you remember, that was F equals to QVB. In fact, this equation is also QVB sine theta, because it's really, the equation really is QV cross B, where cross is the cross product. If you have taken mathematics, you might be familiar with it. But this just means that it gives you the sine component of this thing. So it would be VB sine theta. And then again, if usually theta is 90 degrees, so this just reduces to QVB. Now, these two equations appear different, but it turns out these two equations are just one equation, right? And we'll see how. We'll come from this one to this one, right? And so this equation is F equals BIL. Now, what is I? We know that I is just charge per unit time, right? So if I put this back in this equation, I get F equals BQL by T. Okay, so now BQ is over here. L by T is something. What is it? Length per unit time is just the velocity of these charges that are contained inside this length. So that's V. And then you can see that we have essentially came back to this expression over here. Right? So any questions so far? So this is the topic is usually called a force experienced on moving charges in magnetic field. In B field. Okay, so any questions so far?
No, sir.
Okay, so now, okay, all right, this is the story of the force experienced on a moving charges in magnetic field, but it's not the end of the story. You know, if there is a force that acts perpendicular to the direction of motion, what does that cause? That causes the particle to move in a circle, right? So again, if I have a particle that is moving in this line and I apply a force perpendicular to this direction, what happens is it changes its direction and moves in a circular arc. So suppose if this was the velocity, this is the force, then the velocity becomes like this. What does that mean? Okay, so this force that is perpendicular to the direction of motion is the magnetic force. So we'll call it FP. This means that so why did it move in a circle, the charged particle? Why did it move in a circle? It moved because there was a magnetic force acting on the particle. What does that mean? That means that this magnetic force was solely responsible for providing this particle the centripetal acceleration or the centripetal force, which means that the magnetic force FB is providing the centripetal force, which is FC. Now, we're going to write an equation which will help us to determine the charge to mass ratio of this charged particle, of an electron in this case, right? What does that mean? That means how much charge is contained per unit mass. So this is what we are looking for. Okay, so we know that the magnetic force is QVB, and the centripetal force is mv squared over r. Okay, so what does this give me? This gives me, so the velocities go like that, and this gives me q to m as mv over, sorry, mvb goes over there, rb. Right. So this is at least one equation for charge to mass ratio. The only problem is it is not always easy to measure the velocities of these particles directly. So we can rearrange, we can get rid of this velocity. Uh, so again, this is because if I'm performing an experiment, theoretically this is all well and good, but if I'm performing an experiment, I cannot really measure this velocity accurately. So we replace this with something that we can measure in experiment. For example, the voltage, the potential difference that is causing this magnetic field, electromagnetic field. So we'll write it in terms of that. But before we do that, if I look at this equation, there is a familiar looking term in this equation. Can you tell me what that is? A product of two terms, which is something that we are all familiar with. It is MV, right? So
Sir, why do we
yeah,
have M on the right side?
M on the right side. Oh, sorry, my mistake. It should be just V over RP, right? Okay, now another thing that you can measure is the radius of this circular path, right? What does that quantify? That radius quantifies how much the particle will bend inside a magnetic field or a magnetic force, right? So that makes the radius an important parameter, and so the radius is then written as mv over bq, right? So this equation, this will quantify how much does the particle bend, right? And so it is the radius of the circular orbit. Okay, so now in this equation, we can directly see that there is a very familiar looking term, that is the linear momentum. Let's just use a small p to write that, which is m times v, right? Using this, I can write down an equation for the linear momentum of this particle that is moving in a circle. I keep saying linear momentum because there is another type of momentum, that is the angular or rotational momentum, that is associated to a rotational motion. And even though in this case the particle is moving in a circle, which is a rotational motion or an angular motion, there will obviously be some angular momentum as well. But we do not discuss it in this syllabus, right? So if I write this P is equal to mv, then the above equation transforms as R equals P over BQ. And then I can make P my subject, and then this becomes BQR. For an electron, for an electron, the linear momentum is BER. Right? So B equals BER. Okay, so in this equation, let's come back. Let me just box this one up. Let's come back to this equation, right? Here we see that the radius, because charge to mass ratio is a constant, right? For a particular particle, if it's an electron, it will be a constant, because neither does the charge will change on an electron, or its mass does not also change. So it's a constant, which means that the relation between velocity and the radius of the particle would be directly proportional, right? So this tells me that the radius of the particle is directly proportional to the velocity of the particle. Now, what does that mean? Suppose that if I have a particle that is coming along in this direction, and let's say there is a circle, try to draw it like this. Okay, so here we have a particle that's coming in this direction. This circle that I've drawn, don't be confused, it's just the region of magnetic field, right? Or the region of magnetic field due to which there will be some magnetic force acting on the particle. So what will happen? Suppose that there are multiple same particle with different velocities, right? Suppose first is the case for V1, V2, and V3. So I'm not drawing this diagram again and again and again. I'll just draw it on this diagram. So if the particle is moving with some V1, and suppose that, so let me write it over here, V1 is greater than V2, and then that is also greater than V3. So that means V1 is the highest velocity and V3 is the minimum velocity. So according to this relation that r is directly proportional to the velocity, this immediately gives you that the radius for particle 1 will be greater than the radius for particle 2, that will be greater than the radius of particle 3, because they're directly related to each other. So what path would you expect? I'm going to draw 3 paths. At least I'm going to try to draw those. Okay, so these are not completely accurate, but it will do, right? So these are 3 different paths for these 3 different velocities. Can you tell me which path is for particle 1 or velocity 1, which path is for velocity 2, and likewise which one is for 3?
The rightmost is for V1.
This one?
Yes.
Okay, so this is V1. Then what about this one?
V2.
V2. And that leaves this one as V3. Again, we got this from the fact that for velocity 1, the radius will be maximum. So you can see that this radius is maximum. So suppose if this is the center, then this length is greater than this length, and this is greater than this length, right? So so this would be the relation, and this just tells you that the greater that the velocity of the particle is, the greater the radius will be. And what does that mean in terms of deflection? The greater velocity means less deflection, right? So I'll write that down. Okay, so just another thing. If I draw a particle inside this magnetic field, again, this circle is the magnetic field, and okay, so I don't know if I can draw it neatly, but so this is the path of the particle. Uh, can you tell me when, uh, under what condition will the particle follow this particular path, which is a spiral path? So the particle goes inside the magnetic field and it spirals with a decreasing radius. So the key, the hint is that the radius is decreasing, right? In this example, the radius of the particle, the path that it's following, is decreasing. What does that tell you about the kinematics of the particle? So again, in terms by kinematics, velocity, right? So what would happen? What would happen to the velocity?
It would decrease as well.
It would decrease. So the velocity is decreasing. Not that the velocity is less, but the velocity is at particular value, and then it's constantly decreasing. So when it's decreasing, the radius will also start to decrease, and so it would spiral like this. So this means that a decreasing radius implies decreasing velocity. Or you could just say that the decreasing velocity implies decreasing radius. Okay, so again, let's look at now this equation for the radius. Let me box that one up. Let me bring it to the next page. Where's the next page? Okay, so what's the equation? R is equal to mv over bq. Right. So in this equation, we can see the relation between the radius of the path and the magnetic field as well, which is the inverse relation. So what does this mean? This means that if I have a stronger magnetic field, it would bend the charged particles in a you can say more or in a greater amount, because why is that? Can you tell me? If I have if the magnetic field is strong, the radius is less. What does that mean? That means that the bend is more. And that happens obviously because how can the magnetic field, if the magnetic field is strong, that implies that it would generate a stronger magnetic force. So the particle that was moving inside that magnetic field experiences a much stronger magnetic force for a stronger magnetic field, which means that its path is more likely to be bent more, right? And hence there would be a smaller radius of the circular path that is formed. Okay, so I'll give you a value for this charge to mass ratio that you measure in the lab. For an electron, this ratio is about 1.76 into 10 raised to power 11 coulombs per kilograms of electron, right? So you can see, what does this mean? This means that if I have 1 kilogram of electrons contained in some space, then there would be this much charge acting on that entire surface. So for example, this is a box and I have so many electrons inside this box, right? So of course you would expect a lot of electrons in a mass of 1 kilogram, right? So there are a lot of electrons, and the total charge on then this 1 kilogram of mass is 1.76 into 10 raised to power 11 coulombs, right? So that's what this means. uh, uh, while for a proton, the charge to mass ratio is about 9.6 into 10 raised to power 6 coulombs per kilograms. And you would expect for proton the charge to mass ratio to be quite less compared to electron. It is multiple orders of magnitude less than the value for the electron. So for electron, it's 10 raised to power 11, while for the proton, it's 10 raised to power 6. You expect this because the mass of the proton is quite heavy compared to the mass of the electron. So again, in the same way, if I have a kilogram, a container, and I put all protons inside it, tightly pack them in there, such that the mass of that thing is 1 kilograms, then there would be a 9.6 times 10 raised to power 6 coulombs of charge acting on it. Okay, so one more thing about this. Suppose if I have a magnetic field. So okay, suppose this is the magnetic field. And in this magnetic field, if I have multiple particles, okay? So we have a proton, I'll call it now P. We have electron. And then there is another particle, you're all familiar with it, called neutron. So neutron carries no charge, right? If I have this thing, now these could be either a proton, electron, or a neutron. And this is the magnetic field. Suppose I'll tell you the path of the electron is something like this, right? Can you now tell me what would be the path of the proton, and then what would be the path of neutron?
And the neutron will travel straight.
The neutron will travel straight, so it would go.
The proton will be deflected in the opposite direction to the electron.
It would be exactly. So it would be deflected in the opposite direction. But can you tell me about the deflection? Like, will the radius of this thing be higher, or will it be?
It will be lower.
For the proton?
Yeah.
Okay, so just look back at this equation for radius, right? R equals B V over, sorry, not B, it's M V over BQ, right? So if I write this for proton, it would be mass of proton times velocity divided by BQ, while for the electron, it would be mass of electron.
Oh yeah, it would be more.
It would be more, right? So this is for the electron, and so you would expect a much larger radius for the proton, and it would be deflected in the opposite direction because of the opposite signs of these two particles. So compared to the path of the electron, it could be something like this. Okay, so again, this is because for the proton, this charge to mass ratio is much smaller. So that implies that the radius is much larger. While for this one, the charge to mass ratio is much higher, which would then imply that the radius is much less. Okay, so any questions so far?
No, sir.
Okay. Now let's have a look, slight look at least, at how can I measure this charge to mass ratio. So measuring charge to mass ratio. Okay, so what you do is you take a beam of charged particles, and because of course why we are measuring charge to mass ratio, one of the reasons is that uh, it's very difficult to just have a single electron contained inside something. So it's easier to have just you throw a beam of electrons, multiple electrons, and then find the charge to mass ratio, and that would then from that you can easily multiply it with the mass of the electron, and it would give you the charge on single electron. So in some way you can say that it is kind of like the how we treat density of particles, but it's not really the density of this thing, but you can make that analogy for understanding purposes. Now what you do is you take a circular chamber, and the chamber is in behind the chamber and in front of the chamber there are, so I don't know how to draw that, let me actually do it. Okay, so yeah, this would work. So behind the chamber and in front of the chamber, there are actually the size of these coils is the same, so I'll just use this. Okay, I'll just use one. But there are two coils, front and back of this circular container. It's actually a spherical container, and in this we have a beam, a source that emits a beam of electrons, and because of the magnetic field, this beam of electrons will deflect, right? So